Number 3 is kind of an interesting problem on this week's homework here. It discusses a 10-centimeter long wire pulled along a U-shaped conducting rail in a perpendicular magnetic field. So just deciphering that is probably a big job in itself. But in either case, here's the U-shaped conducting rail. They're sort of referring to something like this. It's a U-shape and, of course, one long continuous wire. And then this 10-centimeter long wire that they're talking about is something like this. So there's like another wire that's just set on it like this. And I'm drawing these little loops here to indicate it's sort of set on there, but it just forms one big long conducting loop. And this distance right here, I'll just call script L here. That's my 10 centimeters right there. So that's what I mean by the 10-centimeter wire. And there's a perpendicular magnetic field, meaning in this problem here, there's a magnetic field which is doing something like this. Perpendicular magnetic field all over the place. The whole loop is completely immersed in this magnetic field. And the wire, that sort of thing. Gives you some more information about the resistance of the rail being something like, 0.2 ohms. So there's a bit of resistance in there. So there'll be some stuff with the DC circuits we did a couple of weeks ago. And it says something about a force of 1 Newton, this force here of 1 Newton being required to cause 4 watts of power to flow in the circuits, 4 watts of power. So it's kind of an odd problem here, but when you look at what it's doing here, it actually relates very well back to number 1 on the homework, in that what you're doing is you're moving a conductor in a magnetic field. So you have a force that you're applying on this parallel wire like this. There's the force right there. And it's also, if it has a force on it, it must also be moving eventually because there's an acceleration on it perhaps. And so there'll be a velocity on it as well. So this wire is actually moving this way. Loop's getting bigger, but it remains a big conducting loop like that. Current can't flow around this. And for some other examples, just sort of the basis of why conductors in magnetic fields generate a current is that there's charge separation inside of this conductor right here. It's moving in the magnetic field. The positive charge will move to one side and negative charge will move to the other. You can figure out which is which using the right-hand rule, but there'll be a potential difference that develops across that conductor because it's moving in this magnetic field. And this potential difference now is going to drive an electric current through this circuit here at a power of 4 watts. So the interesting part about this problem, I guess, is there's just a good analogy between mechanical and electrical power in here. So you may remember this from Physics 141, maybe not, but I'll just tell you what it is here. Turns out that mechanical power is always force times velocity, and this something like that would have units of watts. And if you just sort of keep working on this thing now, there's a couple of things you can sort of develop here en route to getting this problem done. In particular, part A just sort of pops right out of this thing, that the velocity then would be the power divided by the force. So we immediately get that the velocity of this thing would be something like 4 meters per second. So again, the mechanical force, you must pull on it with the 1 Newton that they're referring to generate 4 watts of power. There's the 1 Newton, there's the 4 watts. If you divide the two, you get what speed must be required. In other words, how fast you need to pull this piece of wire here to generate that 4 watts. That's sort of the answer to part A, and it just comes from considering the mechanical power that goes into something like this. The next part of the problem then sort of wants to know, what is the strength of the magnetic field that would require to pull this off? Well, there's a couple things you need to put together, a couple ideas to put together to even begin to address a problem like this. The first one is that the motional EMF, in other words, the potential difference that will appear across this wire is given by this script E here, and it's given by the quantity V times L times V. You can find this in your book, or we did in class, and that sort of thing here. So it's called motional EMF. EMF, of course, means electromotive force, and it's nothing more than volts. This has units of volts right here, but it's nevertheless, if you move a length of wire at a speed V in a magnetic field, this is the potential difference that will develop across that wire right there. So that's sort of the whole idea. And then when this potential difference appears across the wire, you can sort of draw, like maybe if you put a voltmeter here and here, the voltmeter that you put on here then, there's your voltmeter up there, will register a potential difference EMF as long as this wire is moving at a speed V. So there's sort of your motional EMF that you have going on in there. And you can now, if you have a voltage then, Ohm's law certainly holds for an ohmic device like this, so the current that you'd get flowing through the thing would be nothing more than that motional EMF divided by the resistance in there. So you can get that. So the current then would be VLB over R. So now you have an equation for the current. And so we're sort of building into now getting going with the power and so on. So let's just see what happens there. Turns out that just another equation, so you might think of this sort of like is item number 1 on the list and item number 2 on the list. There's the motional EMF. Here's the current that flows. The next item then is that you don't get anything for free here. It turns out that if you're going to pull this thing this way with 1 Newton, the velocity will remain constant at 4 meters per second, but that would be impossible the way I've drawn here. There appears to be a net force on this thing, but like I said, you don't get something for nothing. it turns out there's going to be a resistive force. We'll call it F sub B, F due to the magnetic field up here. So here's the velocity, which is constant, and there's a force this way, and if it was just this picture alone, the force would cause the velocity to continually increase, but that doesn't happen here. The 1 Newton is only applied to just maintain the 4 meters per second at a constant right there. So there must be an opposing force, and this F plus that F must be equal to 0. So the magnetic force plus the applied force, the 1 Newton, are equal to 0 to maintain the 4 meters per second. So that's just sort of another small fact in there. You just sort of have to remember this. There is nothing for free. It's not like I can just take this wire and just flick it with my hand. It's going to keep moving forever all by itself, generating this free electricity. There is this resistive sort of magnetic force in there. And that actually comes from another version of QVB, which is something we used in a previous chapter here, QVB, because we know now, I think we did do this once here, that the force would be Q times V now is delta X over delta T times B. It's sort of recasting the terms. But now if I slide the delta T under the Q, which I believe we did for the Biot-Savart law here, I would get then that the force is I delta X times B, where I is the current, because Q over delta T is current, and delta X there, that would be something like the length of the wire that happens to be in the magnetic field, in this case L here. So there's sort of another form. This is the resistive magnetic force that we'll be feeling out there here. And I think if you look in your book and so on, this form is cast as the magnetic force is I times the length of the wire times B, and in this particular problem, this length of the wire here is just our script L. That's our moving wire right here in the system. This length of wire is the one that's moving the magnetic field. So it would be this force here that's going to resist our 1 Newton force, which is pulling the wire over to the right there. As I said, you don't get anything for free. The magnetic force will resist those efforts here. So if I just fill a few things in here, I have the I, the L, and the B here, but I know what I is right here, then that magnetic force that's resisting my motion here of trying to push that wire over to the right there will be I, which is VLB over R. That's the I right there that I filled in. And this delta X here will be L, once again, the length of the wire, and there's your B right there. So there's a bunch of things that happen here, some things combined here. Again, the magnetic force here will be VL squared B squared over R, something like that. There's the magnetic force that is resisting my motion. So again, this VL squared B squared over R is the resistive force that this thing feels this way when I make the attempt to push the wire that way. So I try to push it to the right, but this magnetic force resists my motion and pulls it back to the left. And if I can balance them, I can keep the wire moving, I'll keep getting my electricity. So there you go. And then the very last step of the problem then is to go back to this mechanical analog, not analog, but the mechanical power here, in particular, that P is force times V once again. Now I have my force here, so the power that I'll get would be the force VLB, but then I have this other V here, so that's just going to make a V squared L squared R, B squared over R. If you put a big box around this, then this is sort of the result and the conclusion that we need to solve this problem out here, that power is force times velocity. Now we have this big power equation, V squared, speed of the wire, L squared, length of the wire, B squared, magnetic field, and there's the resistance of it at the bottom right there. So I think this is the equation you need to complete this problem here. In particular, once again that the power is 4 watts. You have the speed, you have the length, you have the resistance. Now you're able to solve for B. So you can just solve this for B equals to some number in Tesla, and that would be the strength of the magnetic field required to generate 4 watts of electrical power with the 1 Newton force, given that there's a 10 centimeter wire of resistance 0.2 ohms moving in a magnetic field.